Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Madan Muswati from the Software Reliability Research Group, and it gives me great pleasure to introduce Ganesh Gopalakrishnan today. He's a professor in University of Utah, and he's been working for many years on various aspects of formal verification, both techniques and application. Recently, he's been very interested in applying verification techniques to MPI programs, and he's going to talk about his research today.
Thank you, Madan. Hope everyone can hear me, and hope the mic is active and all. Great pleasure to be here at Microsoft Research giving this talk. I know Shaz and Madan and Patrice from before, and Sebastian. Great to see you all. And for others, some of what we do is try to model problems that exist in the space of concurrent programs or concurrent hardware, and then try to build formal methods to catch bugs, basically. I don't know whether this works or not. Otherwise, I just flip the screen. Okay. So the domain that we are looking at, and this work has been going on for about 2 years now, is programs written using this library called MPI, or Message Passing Interface. MPI has been developed in the scientific programming community to program grid machines to perform various simulations. For instance, you might be modeling the physical properties of this gas expanding in a chamber and trying to simulate the physics at a detailed level. But the basic detail is that these MPI programs are highly optimized for various expensive cluster machines, and hence concurrency is an important aspect that affects the performance of the programs as well as the bugs that get introduced. There is a widely felt need in the scientific computing community to have better debugging methods. This is where we come in with our prior experience with model checking methods. MPI is also a success as a standard, in the sense it has become so widely adopted that several manufacturers support it, and in fact it's available in almost all released system implementations. It is also indicative of the kind of APIs that are mushrooming around us, in a sense. OpenMP is this API for programming threaded applications using traditional languages like C, C++. CUDA is NVIDIA's library, which allows people to write annotations on loops to parallelize loops to exploit the fork join concurrency. SHMEM is a SGI library, which is similar to MPI. So all these APIs are perhaps going to be the medium through which many concurrent programs will be written. So it's important to get an understanding of how to handle these APIs, and then do perhaps the traditional kind of model checking or whatever exploration we might do. Pragmatically, there are other reasons. The area of hardware verification is expanding, but in terms of the number of opportunities that are out there, it is still software verification that is giving us this huge expansion of possibilities. In software verification, the traditional research has been in what I might loosely characterize as threading shared memory area, and this message passing area seems to be, especially library-based message passing, seems to be a relatively virgin area. So, but all that aside, I will be showing some code examples of MPI programs, so if you haven't seen one, you might be able to get an appreciation. But at a high level, one can think of, for many MPI programs that is, one can think of the need to compute some mathematical composition of functions applied to some large data set. Well, it may be a map or a filter or a reduce or whatever. You might think of doing these by distributing these functions on different machines and then aggressively overlapping the computations. So this is how many MPI programs look like. Of course, this is a highly simplified view just to keep some mental image of what it is doing. MPI is a library that has 300 API functions, and it ranges from all kinds of simple operations, point-to-point send and receives, to collective operations like barrier or reduce or all scatter or gather. things like that are introduced to make the overlapped computations much more pronounced, and hence the high speeds. So at the end of the day, you need to be able to carry out a large physical simulation and be able to use all the cluster nodes effectively and get correct results at the end of the day. Yeah, so I said much of it. The MPI is on an evolution path. It has it encompasses 300 functions. Most of the MPI programs use about a dozen of these, roughly. But the thing is, each different application class uses a different dozen. So we can't really say this is one popular subset and let's ignore the others. So there are message passing constructs which come in point-to-point or collective. Then there are shared memory escape features that they have built in. And this is actually a weak shared memory that MPI provides as an escape. It has I/O subsystem-based commands, a large set of I/O, and so on. All right. So we are largely considering C++ MPI programs. Although MPI can be used from Fortran or Java or even OCaml, there are bindings for MPI from many languages. We'll look at C++, which seems to be one good choice. Programs are usually written by hand. People have explored the possibility of automatically generating MPI programs for some applications, but that's not the large predominant mode these days. There are groups that are working on optimizing MPI programs by doing source-to-source transformations, and that is relatively successful. If you can think of large-scale data movements between nodes, one could then think of cutting up these communications into smaller chunks and overlapping computation with the communication. So these transformations are local in scope and can be automated. The other thing to keep in mind is that MPI programs do evolve. It depends on the expected life of that software. If it is a serious application, it is maintained and ported to new clusters. And as soon as you port it to a new cluster, all the time constants change, so you have to retune the program. So that introduces bugs. So it all depends on the evolution path of a piece of software, and we don't really know where we are working in that space, although we would like to look at the most serious applications, highly tuned applications that are critical to resources and scientific outcomes. This is where we would like our tools to apply. Code correctness is our emphasis, and this is a funny point to make in a computer science audience, but if I talk to a physics person, they would define correctness as my system model is obeying the law of conservation of energy, things like that. No, that's not the correctness. I really want the code, whatever it does, to be correct according to some specification. Okay. All right, so why is MPI complex? I thought I'll throw in a few slides. Since I'm assuming most of you are not MPI programmers, I thought I'll give you some high-level issues as to what makes this domain interesting or hard. Well, in a nutshell, there are three spaces of concerns that all collide. So first of all, you have the send, receive, fused send, receive, replace, broadcast, barrier, reduce. These are the kind of commands, and this list goes on and on. And orthogonally, you have these commands being able to complete in rendezvous mode, blocking mode, non-blocking mode. Some of them rely on system buffering. Some of them rely on user attaching a buffer. Some of them can be restarted by the user to cheaply reissue a command, and some can be cancelled. So these are other concerns. And the third is the matching rules between, let's say, a send and a receive can be a direct tag-based matching or a wildcard-based matching, or there are communication spaces. So you can think of many axes like that. And the end result is that these are not simple CSP-like or OCaml-like programs for send and receive, but it adds to a lot of detail. Yes?
So what is a replace?
Replace. Send, receive, and then replace the old buffer with the new contents. So in-place destruction. Yeah. So you could use the same buffer to send and then to receive the datum. Yeah.
It's atomic.
It is atomic as far as the local thread is concerned. You don't get to proceed till the replace has been completed. Right. Some of the details I didn't say here are there are these issues about posting a send and then moving on. That is the non-blocking. So when you post a send, till you test for the send completion, the buffer is locked. You can't touch it, but the code can compute. So there are details like that. Yes? Feel free to stop me at any time. Okay. Shared memory escape feature, in the sense MPI has evolved to have a so-called one-sided memory. It's really like a put-based protocol that traditional OS people talk about. sender-based protocol. But anyway, there is an owner process that opens a window, and also these remote nodes that also open the window. So basically, all of them say, hey, let's open a window, but the owner keeps to has the rights to manage that window. All right. It is the one that I'll show you some details, but the basic idea is that between a lock and an unlock on that window, the put and gets that you perform on that window are unordered. They are not statement ordered at all. So you will have to deal with something like a very weak memory model at that point. And one of the success stories from our research group's point of view was to look at a byte range locking protocol that people at Argonne had designed using one of these weak memory regions. And designing locking protocols using weak memory is hard, as we know. And sure enough, we found some bugs using model checking. So this is a benchmark that we could get, and that got them interested in the potential for model checking. Yes?
The shared memory API, is it meant for distributed shared memory or real shared memory?
This is actually a physical, logical shared memory, but arranged to be a local node owning the memory and the other nodes actually sending messages through message passing. So it is not DSM in the standard sense. It gives the conceptual, yeah. So yeah. I'll come to the details in a second. So it is not DSM in the distributed shared memory, but it is a local shared memory, but the global state can be made visible. So when yeah. Mm-hmm.
Can you tell us a little bit more about who are MPI programmers?
Okay, good.
There are people that have, in what kind of background do they
physics.
have? Are they in academia, industry, in research?
Absolutely,
circles?
absolutely. For instance, Boeing and anybody who does Exxon or computational finance, or anybody who wants to use a large cluster resource to get some kind of a model simulated. Biologists use it, physicists use it, atmospheric scientists use it. So there are these very accurate models of the ocean near Louisiana, and they show these real-time videos of Katrina affecting a certain, flying over a certain path. Those are all simulations coupling multi-physics problems. So you can think of, national agencies, NOAA, National Atmospheric Agency.
There are many different...
There are many types of backgrounds with which people come. Yeah, in CS and model checking itself, distributed model checkers have been used, built using MPI. So that's a nice paradigm for. So if you prefer socket-based distributed programming that forces you to address many low-level concerns, with MPI it gives you a higher-level API. So, right. So I'll answer your question about shared memory in one more second. There will be a detailed example. But it is logically a shared space, but there are some restrictions. Okay, so this is the first actual MPI program we can look at and get some feel for how computations are done. So imagine performing an integration under a curve, and suppose you want to distribute that work across multiple nodes. You could ask each node to integrate over subregions, and then one node finally adds up the integrals. And so the MPI program starts with a MPI init, which initializes the MPI system. Imagine the MPI init occurring on multiple physical boxes. After the MPI init is done, each process in each box runs concurrently, and each process knows what its rank in the population of processes is. So process 0 executes this piece of code, and all the other processes 1 through n-1 executes this piece of code. So it's like this data domain based decomposition or work based decomposition based on ranks is a common principle found in MPI programs. Okay, so rank equal to 0 allocates a local variable in its space called integral, and for source equal to 0 through p-1, it is simply performing receive in an iterative loop. Each time it is trying to receive one datum of MPI float from source, and the matching rules for the message are this: it has to match this tag, the message has to be in this communication space, and after that it returns the status. Okay, simple details of who am I receiving from, what am I receiving, and all that. And then it totals the integral. And all the other processes are in parallel doing the subcomputation of the integrals and sending it. So each time the send comes, it's supposed to match one of the receive iterations. So whenever the send matches a receive iteration, the receive picks up and accumulates the value. And the send is sending its own copy of integral from its memory space. It has another variable, integral, sending one float to the destination with a tag in the MPI communication world. Okay, so this program, I can show some simple runs later, but this program is supposed to work as stated just now. And yet this program has a little deadlock. And these are the kind of deadlocks we would like to detect. Okay.
What's in the tag?
Tag is a number like 5, in which case this has to be 5 here.
So it's
Yeah.
tagging what kind of message?
Exactly. These establish priority lanes. So if I have tags with 5 and tags with 6, they are FIFO ordered unto themselves. Yeah. And this could be a wildcard tag, in which case it matches any tag. It could be a star. And the source could be a wildcard, in which case it could be from any source. And this is one source of non-determinism. So I can say I can receive from anybody with any tag. And it's an open receive, a good site of non-determinism and some of the headaches. Okay, so this has a problem because let's look at what send and dest, source and dest will manifest when you iterate. So source starts from source is always 0. Source starts from 0, goes up to p minus 1, whereas the dest starts from else. My rank is not 0 else, so it starts from 1. So already there's a little mismatch. The first offered, first expected source value is 0 because of that, and the first offered dest value is from process 1, which is the dest. So process 0 is collecting, process 1 through n minus 1 are sending. So I'm not getting the first receive from process 0, I can't. So there's a tag mismatch, so this receive will block saying, hey, I can't proceed, I'm not getting a communication from process 0. So that is host. So a program like this, a bug as obvious, even so not very obvious, but obvious as this can be written by a C programmer who starts the iteration from 0 and so on. So there are these reasons for throwing away these bugs. So correcting this, you might write, hey, for source 1 through p minus 1, that's where I'll get the integrals. And source 0 simply sits and eats all the values and accumulates. So this program will now proceed and finish the integration. Okay, so that's one level of detail. Now we have to find these bugs. So I haven't told you the kind of properties we are looking at. That'll come in a different slide. But at this point, we are only looking for what MPI programmers term hangs, meaning can I deadlock this piece of code or hang it? There are a lot of computations that are going on associated with the data. And we simply don't even have the background to appreciate what those computations are in many cases. There may be some simulation of relativistic travel or something. And we are only looking at the reactive part of the programs and currently deadlocks. Okay, so but these communication calls ultimately go into a conceptual box called the MPI Runtime. And this is also implemented differently. On my little Linux laptop, it is basically a bunch of Unix processes come, and then the socket mechanism picks up and makes these communications happen. But MPI implementations vary in terms of how they behave. Some of the MPI runtimes have a separate thread for them, in which case some of these commands will progress whenever you issue them. But some MPI runtime systems don't have a separate thread. It is just a bunch of entry points and a bunch of data. So when you do an MPI send, the data is put into the data structure. It doesn't do anything. When you issue the next MPI command, that's when it pokes or enters the runtime. So it pokes the queue and drains all the pending MPI commands. So why I'm saying all this is when we model check an MPI program, you have to be aware of what the scheduling decisions are going to be. And it's easy. I'll show you an example where you can deadlock yourselves not knowing that. Okay, so you have to be aware of that. Yeah.
So does the semantics of MPI guarantee like a FIFO communication with no loss?
Oh yeah. So MPI is lossless FIFO communication for the same tag and between the same source and destination. That is guaranteed. It'll be a bad violation for a library not to offer that. So it comes with that. Yeah. Forward progress and so on, I'm not sure I have seen a forward progress guarantee in the MPI standard. So there may be unfair schedules possible. And also the other thing is system buffering is variable based on the size of the system you're implementing. If it is IBM Blue Gene or if it is my laptop, the amount of buffer that is in the system to buffer up my MPI send can vary. And so it's possible for the MPI send to have no buffering provided by the system, in which case it forces a rendezvous behavior. So if somebody writes a code that is MPI send, and then receive from each other, send to here, receive. That code will run fine if the system buffering is there. But such a code will deadlock if you port it to a system that doesn't have. So these portability related bugs can be introduced as a result of misunderstanding the communication semantics. Okay. Major differences between threads and parallel programs in MPI. Blue is MPI and black is threads. MPI has processes with the local state communicating by copying. Okay, so you have this nice view of disjoint spaces which can be taken advantage of. And in thread programming, we know that the state is much more pervasive. We have heaps and synchronizations, a different kind of sharing. MPI doesn't have to, most MPI simple programs don't have too much dynamic process creation, whereas in threads, that is usually used paradigm. The control data dependencies are fairly well confined. It's not too bad. Often you do rank-based subdivision of what computation you're going to perform. You might perform some norm computations on the data set to see whether your convergence has been achieved. Has the image been smoothened to the right degree of pixel resolution? If not, you iterate. So those can be easily over-approximated in a model checking kind of framework. You can over-approximate that computation a bit more and get a smoother image. It doesn't destroy the basic control structure. Whereas we know you might be walking in the shared memory world, you might be walking a linked list and decoding all the con cells, so you have to be worrying about more. Aliasing is not at all an issue, again, in small to medium examples, and we know that it's a huge headache in thread programs. So I guess we are able to work in a different space of concurrency, and maybe we can take advantage of these features in doing our job better. Okay, if I'm not clear or going too fast, let me know, otherwise I'll go at the same speed I've established now. Okay, so conventional debugging methods of NPI. Lots and lots of codes, tools out there, very expensive tools out there. One of the companies that does the best tool sets in this area is called TotalView. They supply these hugely capable tools that can deal with thousands and thousands of processes. Look, IBM Blue Gene, if you had to debug an MPI program in IBM Blue Gene, you should be able to view 64,000 processes. It has 64 2 raised to 16 processes. And you should be able to cluster these processes into nice groups and watch them, make them do single steppings and all that. So inspection or simulation based, yeah, it's the bread and butter way of debugging an MPI run. And they are also very candid about the kind of coverage they're getting, because people are not able to find bugs in this, and the codes yet crash on a cluster after a week of run. Simulation with runtime heuristics is another set of tools that are coming from the traditional, more software engineering oriented camp. So there are tools that can schedule MPI processes, but set timers, and based on the timeout, they can say, okay, there's a deadlock maybe. Intel has a trace collector, which is really collecting gobs and gobs of MPI calls as a trace, and then look at the trace file, and then tell nice things about what's going on. But what we are really interested in is more like a model checking kind of approach, where given a certain state space, we want to more thoroughly, ideally, exhaustively search it and find issues or bugs. Okay, so I already said what one needs to verify. Overall computation achieved is the ideal, and in fact some people are trying to execute MPI programs symbolically execute the MPI program to simulate all the value flows and recover this F composition, G composition, H at the end of the day. Well, you can do that if all the plumbings are nice and easily statically predictable, but what about a wildcard or tag matching rules are complex? You don't know who's plumbing where. So we said, okay, we will not look at symbolic execution, we'll look at reactive bugs. But after talking to many domain experts, we finally found this phrase coming out from their mouth: my code hangs. Okay, so let's go after that. Okay, so that's on the properties. Okay, so I have some more real slides, detailed slides, but these are again to establish some background. There are several approaches one could use. I mean, we need not pick model checking as the only approach. One could find many violations through static analysis. So for instance, one could look at the contract that MPI ISEND wants. MPI ISEND says, I'm going to post the data, but the buffer itself is not usable till I see a wait or a test on that buffer, which is in a forward code path. So one could do flow analysis and see whether the code path is covered with wait or a test. And the conditionals are not too bad in MPI, so it can be done. So some of these methods are best done using static analysis. Instrumentation tracing, but finally model checking is the king in terms of going after all the interleavings in concurrency land. But we think that static analysis to support model checking is really going to be good for this area, and I'll show you some examples of how we think that might happen. Ultimately, you have to bear in mind that when a person writes an MPI program, he or she is not at all a domain CS person, typically a physicist or an application person, so they may not even know how to write an assertion. So to create a formal model like in a language like Promla or Zing as a separate activity is kind of very costly and not to be expected for many groups at least. So we want to run the real code if possible. Okay, so again, I have already said this. We will ask for C++ MPI programs. We won't ask for actual modeling. We will do in-situ model checking, meaning run the actual code in place. We may need to simplify the code before running. The main thing is lots of interleavings will happen among the MPI operations. And one thing to keep in mind is that all these MPI operations are happening in different memory spaces. So one could easily imagine and say, hey, these interleavings are affecting disjoint variables. So maybe it doesn't really matter which order in which they happen. I.e., can two actions being commutative be taken advantage of? And that results in this approach called partial order reduction, which is a favorite of model checking people, to explore only the relevant interleavings. And the idea of partial order reduction is portrayed here. So if you have a thread that touches, goes through 3 states, another 3, another 3, you have this explosion of trajectories going from one cube to the other cube's corner. And partial order reduction tries to sort of say, aha, you don't need to consider all these walks. One canonical walk is enough. So this is what partial order reduction tries to achieve, largely at runtime, through runtime techniques, sometimes achievable by static analysis. Statically, you can say, run 1 first, run 2 second, run 3 next. That's enough. But oftentimes, you need runtime information. OK, so we can even address this gentleman's question in the back and look at this example. So this is a small code fragment written in the MPI shared memory programming sublanguage. And process 0 and process 1, let us say, have opened a window for communication using shared memory. And that is not shown here. There is a MPI win allocate happening after MPI init. But then the owners can do an MPI win lock and then do accumulate and then unlock. Okay, maybe more actions between lock and unlock. So it is these actions between lock and unlock that are not ordered. They are weakly ordered. And the non-owner can also do a win lock, accumulate, and unlock, and then maybe do a barrier and then do a finalize. Okay. The semantics are such that it's only this MPI win for the owner. Both the lock and unlock are salient events, meaning this is really seriously taken by the MPI system as a lock being held. For a non-owner, the most MPI implementations say win lock is a no-op. It just throws it away. And then it accumulates all these operations after the lock. And when unlock happens, it has by then created some interleaving of these operations. And then it launches a big packet containing those interleavings to this guy saying, please write it into your shared memory window. So this owner gets to negotiate when it gets into the window, etc. Okay, so that's the semantics of shared memory. It's kind of, I can accumulate in my shared memory region locks and unlocks, and then send it as a parcel, and the owner deals with the locking. So anyway, that's the detail. We're not terribly worried about that. If you look at the this program, init and init really don't have any dependency. You can do the init call in either order. Suppose the process execution is situated in this state, MPI win lock and MPI win unlock, okay, the state before here and here. Now if you launch this process forwards, it takes the lock, okay. So when this lock is taken, essentially this operation is getting disabled at that point. So win unlock cannot perform because it doesn't have the access to the window, so to speak. So this is a commuting relationship. When two actions are enabled, firing one disables the other. That's when there is some dependency between them. This is what partial order reduction algorithms are based on. So in that sense, it's only these two operations that are dependent. And so you can actually do some calculations on this program. And the number of interleavings, if you don't exploit partial order reduction, is 504 interleavings just for this program. It's easy to calculate that also. If you take away the barrier, you can do this factorial times this factorial divided by this factorial based calculation. It's 504. It's very surprising. But with partial order reduction, you can explore the state space using just two interleavings. You try one interleaving where this lock is taken first, and then this MPI win lock essentially gets scheduled here, or you schedule another computation where this lock, MPI win unlock performs, and then this code runs. There's no other sharing. The barrier is completely commutative. You can enter the barrier in either order. So there's a big potential for partial order reduction to shave the number of interleavings, even in a small program. So the trick is to know whether it is like this in larger examples. Okay, so we have really no a priori notion of what MPI operations commute in this sense. So if two operations are enabled, firing of one shouldn't disable the other, or if that doesn't happen, then they should close. Firing one and firing the other should lead in the same state as firing this and that. So we don't know that relation a priori. So what we decided to do was to study the MPI standard text documents and write a formal specification so that we have some notion of this independence relation. So with that view, we set up the MPI 1.1 standard. We set out to look at it and wrote a transition style semantics for a few of its operations. We handled about 20 or 30 operations in our first go. So we wrote these transition systems which said, if you have reached this state, sigma is the set of states reached, and if this is the collective context, this is the process state. The process is looking at a local and a global state components, and it's doing a wait. Under certain conditions, the state moves to this kind of a state. So we wrote a transition system semantics, and actual semantics was not written in that math notation because nobody knows what the math is saying in terms of correctness. So we actually wrote a TLA plus model for these commands. So MPI wait would occupy 2 pages of TLA plus, which essentially says that in some more detail. Okay, so we are at the process of discovering what the commute relation is. We wrote the semantics. Semantics like this are not very known to be matching the actual MPI implementation. So we decided to create an executable environment for litmus test or a simple testing of this semantics. Okay, so maybe by testing the semantics against small MPI programs, we can understand whether it even matches reality. Yeah. Mm-hmm.
Sorry, for the specification of the semantics for that operation, it essentially boils down to basically describe when is the thing enabled and what is the state change. Is that correct?
That's right.
It doesn't include any per se commutativity type of information.
It doesn't. So based on this,
later.
Exactly. Yeah. So having a basis like this, we could sit down and prove some theorems on paper.
And you still need like 80 lines of spec like that to for that. It's so complicated. So when you say wait, whatever, it's including all the parameters, etc. It's like one variant because like if you have like 7 arguments that each combination, then that's or is it like you see what I mean?
We don't carry the data arguments, fortunately, because most of the commands don't depend on the data. But it depends on a lot of side conditions. What if you have not allocated a handle and you're waiting on the null handle? It is a complete specification, and in fact we have cross-referencing. So if you go to page 200, line 10 through 12 of this 3-inch document, you can find it in English. So the student who did that actually took care to cross-annotate it. I studied it over 30-40 pages of LaTeX he produced, and it seems to say what the English says, except very nicely. And so it even has these. So and double wait. So can you wait on an object that you have waited on again? So all these, but the English document is not a oozing list. It gives you some boundary cases and then one main case, but we did capture it all. But the proof itself was not done with this model. No, we haven't reached there yet. We did do the commutativity proof only with respect to a simpler view of the transition system. And so in that sense, our dynamic partial order reduction or whatever is still suspect, but we are slowly making progress in terms of what we are able to do. So this is the semantics, and we did build an executable environment. I have demoed it in the past, but I may not be able to. Maybe I can try later. The student actually built a Phoenix multiple students, they built a Phoenix compiler-based front end for accepting a limited vocabulary of C++ with MPI. And it outputs a TLA transition system for the C program and the MPI calls stitched in. And then we run the TLC model checker. And when the error traces, we can put assertions in the code. If the errors come back, we are able to step the Visual Studio debugger and show the designer the error trace. So this is an independent project, but the idea here is these APIs are coming at us from various places, and who's going to model these APIs? At least we are showing the possibility of modeling some APIs and having a dialogue with the standardization community or the MPI programmers, and slowly evolve a golden standard. I mean, it's kind of irritating that some widely used standards don't have a formal model. So maybe this helps. All right, but that's the end of that. It may have other uses like in test generation and so on. We have looked at that. But based on that, okay, I don't know how I'm doing with time, but one could even confound expert MPI programmers with 5 lines like this, and they won't be able to answer, may or may not be able to answer some detailed questions. Are these message sends going to be in order processed? When can you actually reuse a buffer? When is what is this immediate mode synchronous send? So what I'm saying is a litmus test calculator like that runs glacially fast or slowly in the TLC system. Model checking speed is not high, but that's fine. You can even check programs like this, and it produces useful traces. So it's like Sebastian's and my prior work on shared memory testing. You don't need large litmus tests to find corner cases. So that's that use, and it has some small GUIs and so on. But that's not the main point of the talk. Okay. So the next issue I want to bring to our attention is, well, what is the notion of dependency for MPI? Well, I briefly mentioned that the shared memory spaces work in a certain way. But now coming to message passing, the notion of dependency for MPI is more dynamic. It's more runtime dependent. And why is that so? We can look at a simple example where there is a wildcard receive, meaning I can receive from anywhere, kind of a command here. And there is a sender here, and there is a send here. So really, at runtime only we can tell which sends are going to match which this receive. Okay, so this send may have the right tags, everything that can potentially match this receive. This receive may have has a wildcard, so you can receive from anybody, but only by executing an actual program can we safely predict that this is going to match. So we don't know whether these code paths are feasible or not precisely a priori. So if we say that this send is going to match this receive, and then go ahead with the model checking, we will later find that oops, we overlooked another interleaving where we could have done this statement instead and match that receive. So this is this classical problem of not knowing enough into the future and making a pessimistic assumption or doing it incorrectly. So if you make a pessimistic assumption, we will say every possible send in the universe will match this receive. If you don't make that possibility into account, you will overlook some dependency. So this is one reason why we found that the needs for MPI in terms of its partial order reduction and what Flanagan and Patrice Godfrey have proposed are a very nice match. So some of the details of the MPI dependence are in this slide. I won't go over it too much, but basically I want to turn your attention to again this notion of commutativity, where what their paper shows is if you have two actions from the standard view of shared memory world programming, and if you want to answer whether this aj plus ak minus minus commute, okay, it is so if j equal to k or j not equal to k. So if j not equal to k, you can do this and that, or that and this, and you get the same array. But who will tell you whether j equal to k? That's a runtime information as best in the most accurate form. So this is why we find the dynamic partial order more applicable. And so we have really not changed the algorithm much. We just implemented it as befits MPI. And the main flow of the algorithm is as follows. We march a process. Let's say this is how our algorithm works. We march a process, let's say the blue process, then we march the green, then we march the red, then we march the green, and we are about to march the red. Okay, this is where we are. This is the current state. What do we do now? We see what action is going to fire. The red action is going to fire. Then we look up the stack to see which is the action that it is closest, where is its closest dependent. So we find that the green is not dependent. Of course, we don't compare a process against itself. That's meaningless for interleaving. So we find, this blue process has an action, this action which is dependent in a non-commuting sense. So then we'll say, okay, we have to mark this point and say, when we later replay this, the red process must be allowed to run from here, because the blue-red happened here, maybe the red-blue will happen later when we mark it this way. So this is why the DPOR says, okay, next time you are replaying this, when you're here, don't run blue, don't run red. So this is how DPOR works. That is sort of maintained here. Okay, so, but the idea is that's one nice paper algorithm under certain assumptions. Now we have to make it work for MPI commands, knowing that the MPI scheduler and MPI runtime behave in a certain way. So this is the next set of tricks we need to understand. How do we instrument the program? This is a big problem. Well, fortunately for MPI, this is easy. For every MPI function, any MPI library comes up with a PMPI same function. And they have provided these carbon copy functions for profiling purposes of MPI. So we can easily use this existence of PMPI. What we do is, whenever MPI send needs to be instrumented, we override the existing MPI send with our own MPI send, and then have a chatter in the background saying, scheduler, can I launch MPI send or not? And the scheduler says, go ahead, launch MPI send. We call it PMPI send at that point. So the PMPI send has the same function, it comes back. So we can sort of override these functions, and the instrumentation is just the act of supplying our own replacements and linking in. And then, yeah.
So you assume that you have a central scheduler. You run all your
Yeah. Exactly. Yeah. So we have to. In my laptop, for instance, there'll be n Unix process modeling my MPI process. I started n+1 first process and establishes TCP sockets with everybody. And then the scheduling engine is every time the process action is trapped by the scheduler can let go a bunch of user processes. They all run, but then the scheduler waits for these processes to come back. It's a simpler implementation of the scheduler, and then launches somebody else, waits. Then it plays this scenario out, like I showed. Once the end of the scenario is reached, it kills the world. It kills all the processes. It wipes out all the sockets, but it keeps the stack information with the backtrack sets. And then it says, aha, let me replay this scenario, but here I'll run the red now. So it's sort of a stateless blind beast which reruns repeatedly and tries to manifest. But I'll show you what the costs are and so on, but that's the conceptual algorithm. Yeah.
So an MPI send
Yeah.
implementation can
Right.
be fairly complicated.
The code can be, yes. Mhm.
And do you actually reuse some of the implementation?
Oh, in the sense, yeah. PMPI send is another name provided by the MPI system as a binding, the linker. So if the user wrote PMPI send instead of MPI send in the normal MPI program, it would work the same. So we take advantage of the fact. We write only a small stub which says, let this function override MPI send's name, and then that does the chatter with the scheduler, and the scheduler say, go ahead comes, we call in our little stub PMPI send, which dives in and does the same work as MPI send. So we just trap this function and use the function f prime which the system provides to achieve the same work. But trapping f, we don't let go f prime till we have made sure it is good to fire f prime. So that's the thing. So each time all these appeals come to the scheduler says, these guys must go ahead, call their PMPI, wait for them to come back. And yeah. All right, so this is going to be kind of expensive, but we will show some ways to combat the problem. But the other concerns are, like I briefly alluded, since the MPI runtime system doesn't have its own thread to schedule MPI actions, we should take care not to get wedged in the scheduler in the MPI runtime system. And in the interest of mental cycles, I will quickly walk over an example of how it might happen. Okay, but you walk away with the spirit of how it happens and how we solve it. It's a simple cure. Okay, so suppose we have this example and we want to do our model checking, and we have executed this much. Okay, nothing interesting happened. MPI init went, it says go ahead, MPI launch MPI init, it came back, launched it. This game launched, this game launched. Okay, at this point, the scheduler has let P0 owner do a win lock. So the scheduler says, aha, I have acquired, P0 has acquired the window. So P0, the scheduler records P0, the window is locked. And it has to, so the scheduler has to sort of mimic the MPI semantics a little bit. Okay, so now what came? MPI win lock came, but remember the non-owner's win lock is a no-op, so the scheduler says, go ahead, do it. Then accumulate came, some accumulate operation, no problem, do it. And then this came, nothing happened. And then let's say that P1 issues a win unlock at this point. So it is sort of half issued, half colored. At that state, the scheduler traps it and then says, okay, it knows that the window has been locked, but that's fine. We need to still make P1 really fight for the window in the MPI system, so it has no choice. Go ahead, issue. So we just P1 is still in a P1 is in a block state conceptually because P1 cannot proceed. The window is locked, but go ahead and launch the PMPI window lock, so it goes into the MPI system. There's nothing else that you could do. Fine. Then this window unlock comes. P0 issues. Okay, now the window is about to be freed and all that. But here is where a little delicate dance happens. Okay, recall that P1's PMPI winlock has been launched, but P1 has not reported back to the scheduler yet because P1's winlock is sort of waiting for the window to be available. Okay, all right. Okay, to keep things, okay, yeah, this is what I said already. The scheduler model is let go, come back. If I now allow P0's MPI winlock to issue, it may zip through the progress engine really fast, boom, and then come out. P0 has not, suppose the P1's win unlock is slowly traveling over a slow wire, it is not there. So the P0 winlock is allowed to issue, and let's say it zips through the progress engine and comes back. So now if that happens, then P1's MPI win unlock stays in the progress engine, waiting for somebody to push it into the progress engine. There's no separate thread, remember? And there's only, that gets pushed in only when somebody else enters the progress engine the next time. Who is going to enter the progress engine the next time? Well, if we issue MPI barrier here, that will enter the progress engine. But our mental model is not that. We won't aggressively issue one process 5 steps ahead. We have to wait for P1 to come back home before we allow another process to issue. So in a sense, the P1 event is stuck in the progress engine waiting for somebody to poke it through. So this is kind of too fast, but that's the idea. There's no separate thread. If I show you the fix for it, you will know exactly what I'm talking about. The fix is not too hard. So the fix is, this is how we trap MPI win unlock, just as an example. So when the user calls MPI win unlock, the code call comes here, and it says send to socket saying, tell the scheduler this is what I'm going to do. And then while receive from socket not equal to go ahead, so the scheduler has the option to keep this command in abeyance. So in this case, P0's win unlock is kept in abeyance. So then P0 is forced to do MPI iProbe. This is a poker action. So it's saying while you're not ready to go ahead, just issue some command into the progress engine, even though the code may not have it. Poke, 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 poke. So this poke commands, MPI probe is like a no-op. It simply does some innocent observation of the system. But in the process of entering the progress engine, it pushes the P1's iProbe, which was the MPI's P1's win unlock, which was held. So when this poke happens, P1's win unlock gets processed, and then P1 comes back to the scheduler, and then the P0 can be allowed to fire again. So this is a delicate compromise between how hard a scheduler we want to write and the innate absence of threads in the MPI runtime. So but the bottom line of the story is instrumentation and the scheduling doesn't happen magically. There are these gotchas that we learn the painful way while we build the system. But the idea is the solutions may be MPI library specific. We don't know which MPI library handles progress in what manner. Some MPI libraries may be so generous as to provide a separate thread for it, in which case nothing like this happens. Yeah.
So this probe is something which MPI provides?
MPI provides, yeah. MPI provides it, and we discovered that as the most innocuous command to issue, and it has the property that it enters the progress engine and leaves no side effects. So it could be even time of the day. If the time of the day enters the progress engine, you could do that. So, but a better thing would be for the MPI library to provide a broader API so that the programmers might do something more clever. That's not there yet. All right, so how does it work? I will show tiny runs of the execution. The trapezoidal integration code I showed you for, I forgot how many processes, will find a deadlock. But the shabby thing is 33 interleavings exploded 9 seconds after fixing that range error. You remember that it has a deadlock, so if deadlock is found quickly. After you find the iteration should go from 1 to n. it runs to completion 9 seconds, but 8.4 seconds are taken restarting and killing the MPI processes. So there's a big havoc that we are wreaking on the MPI system. There is another code which comes by the name of Monte Carlo computation, but it has gutted out the pi computation details out of it. We just got it from, it's a short 30-line, 40-line C++ program, but with 9 or 10 hard to parse MPI commands in it. It found 3 deadlocks that we didn't expect, but maybe we don't really want to say that this is a violation of something important. It's somebody's test code, maybe. We're not there. But again, for 3,427 interleavings on the fixed code, taking 15 minutes, 0.5 minutes, but after 15 minutes are spent restarting. All right. And then the byte range simply has too many interleavings. Okay, so first order of business is don't tear down processes and rebuild them and re-execute. It's too much of a price to pay here. So what we thought of is, well, and I'll show you a quickie demo of that, yeah.
These programs, they all terminate, or you force termination?
They terminate. Okay, good point, yeah. All MPI programs are guaranteed, is supposed to be written with an MPI init, then blah, 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 MPI finalize, called collectively. So these are all required to be terminating computations.
And in these experiments, you let them run?
You let them till everybody faced MPI finalize. And our deadlock detection is quite simple. When we find where somebody is at MPI finalize and the others are not reaching MPI finalize, there's a deadlock. But real MPI programs may have perverse loops that make it loop inside. We don't have cycle detection yet. So it can hang badly too. So yeah, go ahead.
So how difficult would these bugs have been to find through random exploration?
Okay, yeah. So in good question, we really have not done a controlled experiment to that effect. For the Monte Carlo thing, it will deadlock even in a random exploration. Even for the trapezoidal, it will. For the byte range, it is more interesting, and I doubt whether it will happen. Byte range locking was a serious example which sort of tried to lock details, but we had to find a very interesting scenario of threads running. Maybe 3-4 context, what is it? 3 bounded executions might find it, is my thinking. Yeah, it's not too deep yet. Yeah, we are not there yet. So the thing is, we said, okay, suppose we limit our ambitions just to deadlock detection. Can we afford to not reset all the data and just jump back? So before we reach finalize, we'll just put an artificial collective go-to. Everybody goes to their initial state and simply runs. So sort of reminiscent of what people call the Chinese postman tour. It's not like that. But Chinese postman tour is, suppose you have connectivity in a directed graph in a certain way, and you want to cover all the edges, you have to repeatedly visit certain vertices just to get to some edges. So it's used for internet connectivity testing and so on, Chinese postman tours of directed graphs. So the idea is, suppose we launch the control back to some point and come back in. Well, then trapezoidal finishes in 0.3 seconds. This was 9 seconds before. Monte Carlo finishes in 63 seconds, 15 minutes. So maybe we can cheat and not clean up the state entirely and jump back quickly. So this is one thing we want to study. Lots of ideas, nothing tried out, but DPOR simply says this is the best precision in terms of interleaving search. Can we play with the independence matrix? So we have a certain pristine independence matrix. We won't use it all. We'll say these spots are send and receive collisions will be examined in this run. We will allow everyone else to commute. So vary the precision of the dependency relation may avoid some interleavings and backtracks. Static analysis might help us. Since these are programs with not too much control data dependence, static analysis might remove some blocks for us. This is waiting for us, waiting disaster for us. There are 2-3 nested loops in many programs, because you can imagine you're going over several dimensions of a data set and communicating things. So these loops will have and unravel all these MPI commands. If you interleave all those commands with all the other guys' commands, the interleavings will shoot up. So we might have to selectively peel out the loop iteration, saying, for these iterations, initial iterations maybe interleave. Then the other iterations don't even instrument. Just let it happen in the MPI system, but let the commands. Maybe not.
So
yeah.
you're saying these interleavings actually, even with dynamic partial reduction.
Okay, good. We haven't really tested our on a real test set. But suppose the 3-nested iteration has a command that doesn't commute with another 3-nested iterations innermost command. Then in the unravel setting, every instance of this might have to collide. We don't know. DPOR may or may not be able to. But selective search is what I'm hinting at. We might want to selectively interleave. This has actually been implemented. We have evaluated the numbers. The user might write a code in this phase. Code goes through this phase and then this phase. So put barriers and let the DPOR just look at the space between the barriers. We've had to do things like that. And but okay, we just have gone on a certain limb and we said MPI programs are hard. People are making mistakes. We need to run on real codes. Static analysis can only do so much. Maybe there is interleaving, full interleavings like in a model checker may be necessary. So then we have found a certain approach that has been implemented, and it's going to be studied in the coming few years in terms of its potential. I think I will run a quick demo just so that you have a feel for the kind of programs that have been run, but otherwise pretty much. Okay, so this is the length of the code and all that. So this is how the Monte Carlo integration code looks like. This actual code was run. So nice thing is we didn't have to touch the user's code. It runs as is, which is the best thing. Okay, so all MPI programs has its main, declare these variables and status. Okay, so this MPI init is being called by every process, however many there are, and each process is asking MPI com size, how many processes are there, so they know that, and then it says com rank, meaning what's my rank in that group. Am I the 8th process out of 16 or 9th out of 16? So they know that. Then what it does is then it does a subdivision based on rank. So if rank is less than, let's say 5 server, all those processes do this computation. And then, so many processes are doing this send and receive all concurrently. And then else if rank is some particular number, so that process does this computation, MPI receive, MPI send and all that. Else like that. So you have this ranges of processes, and all these processes are doing this work. And then there is a finalize. Okay, so this is the actual MPI program. And the nice thing for us is, when we started a year or two ago, we were handwriting Promula models for these programs, and we were not sure what to model, what not to model. So at least we have gotten over that problem. And so this, again, small blind test, but when we run ISP is a name for In-Situ partial order, MC, buggy. So we say ISP and then give the socket number to start allocating TCP sockets for process execution, give it the binary, and then which machine to run on. And then it has, okay, like in demos, I don't know where I am. I think this is not the right directory I'm running in. Okay, this is the Chinese hack, which only runs one code. Okay, so I should be in the non-Chinese hack. Okay, so CD ISP, CD. Sorry. Okay. Okay, so this is the actual one, and yeah, I found a deadlock after some number of iterations. So it finds a deadlock, which is basically that there's a while one loop. Popular programming style, somebody writes a while one loop but forgets to exit the while one loop, and that's a while one loop that ended up hanging. All the others had finished and gone home. This while one loop didn't. So fine, that's all I can show here. Then once it is fixed, MC fixed. Okay, now this is how it's interleaving. So each of this is a complete interleaving till the MPI finalize, kill all the Unix processes, reconnect the pipes, and then start again. Clearly, a lot of this pauses are because it's spending time killing processes and reconnecting, and it takes a long time, like 15 minutes to finish it. So we did this what we call Chinese hack, which is the Chinese postman hack. We just said, let us try this, and it works for this example. We can study it to death and find out that it is working. So I can run only one code. This is hardwired for MC fixed. So that's how it runs, and so you can see there's a big speed up if you don't tear down processes. And
in this case, the Chinese hack is
basically just running in one after the other, right? That's right.
This Chinese hack is saying, yeah, go up to the MPI finalize, not quite the MPI finalize, stop there, and reset all the user variables, and jump back to the state just after init. And then that code also resets all the user state.
How do you jump back to that state?
Yeah. We just jump back every.
You have something for that application, or you use checkpointing, or?
Oh no! At this point, we are not even checkpointing. We are simply chewing on the user data. The user data may get so mangled, you may not recognize this. If you are doing image processing, the faces may be all contorted and all that. But we are thinking that we don't need to clean up the user data that much for deadlocks. We have to make sure that the user variables are not so degenerate that you divide by 0 and pointers go out of reference. So what we had to see is, in the MPI system state is not being reset. We assume that if the user wrote the used the MPI system wisely from MPI init to MPI finalize, the MPI system must be in an equivalent state. But if the user is forgetting to deallocate certain things, this is a common bug in MPI. They can allocate a communicator and forget to free the communicator. But many programs don't see these bugs because MPI finalize cleans the world. But in this approach, it might have an advantage. We don't do the finalize, but we are reissuing the execution. So resource leaks that we are causing in the MPI system may surface if you do the Chinese hack. So there may be some reason to go after this. And it seems to speed up, but we had to do this carefully. So static analysis might help us figure out, clean up these and these variables. They are participating in the control. The other variables are simply flowing through send receive. They are not being looked at. Do the minimal cleanup so that you don't divide by 0 or whatever, and then maybe. Okay, MPI checkpointing is a topic that many people are pursuing. The initial read in that literature told us the checkpoint size may be very large. These may be global checkpoints of the processes, images, and the runtime of the MPI, and we don't want to go there if we can avoid it.
You just need one checkpoint, right? Like
fork. Yeah. If we can figure out a way to do the init, like in the Verisoft, you used a fork to spawn off. If there is an equivalent of a fork here, we might use that. But otherwise, this is just recomputing the integral multiple times or whatever. Okay, so that is the end of this presentation. Hope the high-level ideas stood out, and I'd be happy to talk about future plans. Okay, thanks. Okay. Yeah, and we're happy to take questions even after I go back, or even give you this code to look at. The ISP code itself is a small tarball. I could install it in my laptop in 10 minutes yesterday. All you need to do is get mpitch from Argonne, click on it, make. It compiles in 2 minutes. And if you're in MPI programming, and then ISP is another tarball, and then it runs directly like that. Okay. Yep.
So how many MPI programs are there out there?
Oh, yeah. A lot. I mean, the community is large. Even the MPI programmers is a huge number. Each university has physics departments, chemistry students. All these students are writing MPI code. Yeah, many of them.
These programs are big.
These programs,
they are small. Like the example, it's possible to kind of most of the complexity in writing an MPI program is hopefully not to get these wild masses there hacking concurrency code, right? They must use patterns or something.
They do use patterns. They use
it's like
that's right. Yeah, absolutely.
Experts cannot do it. So
that's right.
Why would a chemistry student do it?
No. They use pre-existing application level libraries. This is another big win for a dynamic method. There will be these linear algebra code packages or other diffusion equation packages. They just call those APIs. They don't call MPI many times, and the MPI calls are happening within. And any approach which uses hand-build a model won't work. So runtime based, it traps MPI calls wherever they may occur. This is a big advantage I see. Yeah. And the code base, and And I visited Supercomputing is another conference I go to, lots of goodies and a lot of free things, but they also have all these communities that large cluster centers that produce pie charts of mix of commands and results in terms of errors and all that. Yeah. The other thing is platform validation. MPI platforms, MPI implementations are not guaranteed to be right. Especially when somebody ports it to IBM Blue Gene, there was articles on how they ported the commands so that this idiosyncratic architecture could support MPI and so on. So one way I had to finally say, is this even MPI? And maybe the litmus test that we created may be slightly useful then. I mean, you have all these little MPI semantic routines, so we could say, hey, after this and this command, this outcome is expected, and do some platform validation, but harder area. Yeah. Yeah, and yeah, right. Yeah, there is a conference, Europe EVM MPI, which is held in Europe every year, and we have published twice in that. It's a very applied conference, so maybe we'll know the community better that. And right.
And how complete is your ISP with respect to MPI?
Oh, very, very minimal at this point. Slowly growing. Right now, ISP supports, the first ISP had only MPI send and receive, no collectives, and no wildcards. But now we have wildcard communication, and one-sided memory, and I would say still 20 commands or 15 commands out of 300. Yeah, so we will just omit huge chapters of MPI. IO system we won't touch. It's kind of hard. MPI has derived data types. That's hard. So we will just try to, go slowly. As since Patrice is here, I can't resist this. Another project in our department student looked at pthread programs. Okay, the same approach. Pthread programs are hard and all that. So, but look at terminating pthread programs. So parallel file scan is a pthread program that simply says scan a huge file from multiple pointers. So it's a simple thread parallel. So we actually took those from SourceForge. What the student has built is a wrapper for pthread functions, very similar, and create an executor. There's a scheduler, and this actually worked in the sense we could actually find some uninitialized synchronization variables and so on. And the one nice thing is about DPOR, stateless DPOR is, look, it's like an exponential tree being walked by following different interleaving recipes. We could just ship these recipes across and let others explore. Multiple processes explore. You don't need to have one process explore all this. So we did that, and this was the arrangement. Just have an extra CPU. This worker has pent up a lot of work in its backtrack set. We take a worker's backtrack set size to be the amount of work pent up. When it reaches a certain threshold, it says it needs a handoff. So it tells the load balancer, where can I send this work to? The load balancer says, here. So idle node B. So this sends that trail recipe, and it lets that process recursively do that DPOR from there, and then finally says, I'm done. Okay. So in principle, a clean, easy, embarrassingly parallel algorithm. Look what happened. Well, we did 2 experiments on egg and several experiments. These are close to 1,000 lines of code, pthread, and this is not too shabby. The hand instrumentation work is yet to be done, but we got flat speedups on AGET and BBUF initially. So as we increased the number of nodes, nothing happened. Parallelism was not there. So we had to see why. I mean, so this is stateless search is both a blessing and a curse in the sense when you have stateless, soon those guys might be exploring the same paths as you. Okay, we had no control over that. So we devised a simple heuristic for work ownership that seems to work on some examples. So when we do a backtrack set update, when action B depends on action A, we don't put B in A's backtrack set alone, but we climb the whole stack and put it wherever the dependency exists. It's a kind of a crude hack, and it seems to certainly work. And it seems to be owning a work in a certain sense. I can show you more. This was part of our spin presentation. But we did finish an 11-hour job in 11 minutes on 60 nodes. Okay, so we can get such, but this is parallelizing maybe a hugely inefficient serial algorithm, but parallelism is always the pinch of salt, right? If you take the worst sequential whatever or exponential whatever, it's easy to parallelize it. Hopefully we are not there. So this has promise. The work is really waiting for the front-end instrumentation to be a bit more decent, and even this strategy has looming disasters like loops and other conflict. So you might be accessing multiple data kinds, and you may not keep track of. Okay, so this is in progress. The parallel version has been published just because of its speed up and the heuristic. The sequential version is under development, even though that is the core of the parallel. All right. So yeah, so thanks for your attention. I am sold on DPOR, even though you are not, but even that may need some tuning with static analysis. Okay, thanks. Okay.